Welcome to today's deep dive. So, if you just look at a chest X-ray,
Which is really just this, like, messy grayscale landscape.
exactly,
Yeah.
it's just shades of gray, and a single tiny pixel-width shadow could literally be the difference between a clean bill of health and, well, a life-threatening pathology.
Yeah, and we historically rely on human radiologists to decode that gradient perfectly, every single time.
But they're completely overwhelmed right now. I mean, imaging volumes globally are just exploding.
Oh, absolutely. And burnout in the medical field is skyrocketing. So the industry is, rushing to offload this immense cognitive burden to AI.
Right, automated radiology report generation,
Oh,
RRG. Which sounds great on paper, but the mission for today's deep dive is to look at why current AI systems in this space have a pretty terrifying vulnerability.
yeah, they confidently hallucinate.
Confidently, that's the scary part.
Exactly. I mean, these current models, they'll generate perfectly formatted, grammatically flawless medical reports detailing conditions that just do not exist anywhere in the actual scan.
Which is a massive problem. Because a human doctor reading an AI draft needs absolute mathematical certainty that the text actually maps to visual evidence.
Right. A confident hallucination is infinitely more dangerous than an AI just saying, hey, I can't read this image.
So to unpack this, we are looking at a cutting-edge research paper today. The title is quite technical. It's called Enhancing Reinforcement Learning for Radiology Report Generation with Evidence-Aware Rewards and Self-Correcting Preference Learning.
It is a mouthful. But what makes this paper so revolutionary isn't just that the AI gets a little better at reading X-rays.
Right.
It's that the AI has basically been given the ability to explicitly show its work and, importantly, to self-correct its own mistakes before a doctor ever sees the report.
Okay, let's unpack this, because before we get into the solution, I think we need to understand why the previous AI models failed so badly.
Yeah, we have to look at the baseline problem with how we grade these models, reinforcement learning, or RL.
Right. Which is usually great for, like, playing chess or robotics.
Exactly. But in RRG, previous models, like 𝗚𝗏, for example, they rely entirely on what researchers call report-level rewards.
Okay, report-level rewards, meaning what exactly?
Meaning they use these really broad language metrics to grade the AI. Things like BLEU or RADCLIQ. They look at the whole generated report at once.
I mean, that sounds kind of like grading a student's complex 10-page essay by just slapping a B- on the front page.
That is a perfect analogy. The student gets the grade, but they have absolutely no idea if they got the core thesis wrong or if they just used, bad grammar in paragraph 3.
Right, it just measures n-gram overlap, doesn't it? Just calculating how many sequential phrases match the human-written ground truth report.
Exactly. 4 words in a row match, you get a good score. But if we connect this to the bigger picture, in a clinical setting, an AI cannot just write a plausible-sounding report.
It has to actually be right.
Yes, it must provide evidence-grounded guidance. If the ground truth says the patient has severe pleural effusion and the AI writes, the patient has no pleural effusion.
Wait, it literally inverted the diagnosis.
Yeah, it completely inverted the clinical reality. But a metric like BLEU might actually score that sentence pretty high because, hey, most of the words match the sequence perfectly.
Oh, wow. So the AI gets a positive reward for syntactical similarity, even though it just made a catastrophic medical error.
Right. Because the feedback is so broad, the AI naturally takes the path of least algorithmic resistance. It learns to mimic the stylistic cadence of a radiologist without actually learning how to diagnose.
So since broad grading clearly doesn't work, how do we teach the AI to point to specific visual evidence?
Well, that introduces the first half of the paper solution. It's called the GEAR module.
GEAR, which stands for Group-Wise Evidence-Aware Alignment Reward.
Right. And instead of evaluating the final text string, GEAR evaluates the model's internal visual attention using DRMs.
Disease-grounded response maps, which are basically...
They're essentially heat maps. GEAR compares the AI's prediction against the ground truth report, but it doesn't do it all at once. It uses a tool called CheckSpurt to break the AI's predictions into 3 distinct groups.
Okay, let's go through those. What's the first group?
First is true positives. The AI got the diagnosis right, so GEAR rewards precise spatial grounding using an IOU-based loss.
Intersection over union, right? Walk us through how that specific calculation works here.
Sure. It calculates the area where the AI's predicted heat map overlaps with the actual ground truth bounding box. Then it divides that overlap by the total confined area.
So if the AI correctly spots an enlarged heart, but its heat map is just smeared across the entire left lung too?
Then the denominator, the total combined area, becomes massive, and that drives the overall score way down.
Oh, I see. So it demands spatial economy. You have to point exactly to the problem, not just the general zip code of the problem.
Exactly. Now, the second group is false negatives. This is when the AI completely misses a disease.
Like a subtle lung lesion or something?
Right. And to fix this, GEAR penalizes the omission using an MSE objective. Means squared error.
Wait, why switch to MSE? Why not just use the overlap metric again?
Because in a false negative, there is no AI bounding box to overlap. The model completely ignored the disease, so its heat map is totally blank in that area.
Ah, right. You can't overlap with nothing.
Exactly. So MSE measures the difference between that blank map and the intense, high-signal pixels of the ground truth. Squaring that difference creates a really aggressive mathematical penalty. It violently recalibrates the model to force it to recover that missed evidence next time.
Which makes sense.
Yeah.
Okay, so that leaves the third category, false positives, the hallucination.
Probably the most dangerous one.
So the AI confidently writes down pneumonia for a perfectly clear scan. And the paper says GEAR suppresses this unsupported claim by penalizing the response energy in irrelevant regions.
Correct.
But wait, I have to challenge this for a second. If the AI is generating the report, how does it know it's hallucinating a false positive if it doesn't have a perfect answer key?
What do you mean?
Well, human radiologists aren't sitting there drawing exact pixel-perfect bounding boxes for every single raw X-ray in these massive training data sets. So where is GEAR getting this objective visual truth?
That is a fantastic structural question. Because you're right, if the model just graded its own visual attention, the whole thing would collapse into confirmation bias.
Exactly.
So to bypass that, the researchers use a pre-trained vision language model, specifically one called MAVL.
MAO.
Yeah, medical vision language pre-training. MAVL has already been rigorously trained on vast data sets. So during this process, its weights are completely frozen. It acts as the impartial mathematical referee.
Oh, okay. So MAVL reads the text in the image and says, here's where the evidence actually is.
Precisely. GEAR feeds the raw X-ray and the human-written ground truth report to MAVL, which outputs an objective reference map. Then GEAR compares the AI's internal heat map to MAVL's reference.
So if the AI is hallucinating pneumonia, its heat map is just firing randomly into empty lung space.
Right. And MBL's map is completely dark there. GEAR sees that massive discrepancy and aggressively penalizes the AI for generating an unsupported spatial claim.
Okay, so GEAR essentially fixes how the AI looks at the image. It physically forces the model to anchor its words to verify pixels.
Exactly.
But I mean, anchoring to the image doesn't guarantee the text actually makes sense, right? How do we fix the actual text it generates?
That is the perfect transition to the second major innovation in this paper, SPL.
Self-correcting preference learning.
Right. Because RL policies are inherently noisy. The AI might spot the right pixels, but the initial draft it spits out could be totally garbled or contradictory. SPL fixes that by having the AI generate multiple draft observations.
Specifically for candidate reports, right?
Yes, 4 distinct drafts for the exact same image.
Here's where it gets really interesting to me. This multi-draft approach is exactly like a hospital hierarchy.
Oh, I like that. How do you mean?
Think about it. You have 4 junior doctors, the multiple draft observations, standing around a light box throwing out ideas. They're all looking at the same visual data, but some interpretations are right and some are wrong.
Yeah, one of them might misinterpret an artifact as a mass.
Right. And if you just average their notes together, you'd get a totally contradictory, dangerous patient chart. SPL acts as the chief resident, filtering out the bad guesses.
That is a brilliant analogy. SPL uses a disease-aware preference dataset and a dual threshold sample selector to play that chief resident role. It looks at the statistical entropy, the variance, across those 4 drafts.
So if 3 of the drafts confidently say there's a pleural effusion, it keeps that claim.
Yes, it establishes a high confidence threshold. But if one draft randomly hallucinates a pneumothorax that the other 3 ignored, the selector flags the anomaly and drops it. It filters out the untrustworthy noise.
But a bulleted list of filtered facts isn't a hospital report. So what's the final step? GPT-5, right? Like the senior attending who writes the final patient chart.
Spot on. It takes the surviving, trustworthy data and feeds it to an LLM. They tested several, but GPT-5 worked best. It synthesizes a clean, refined report without any human supervision.
But wait, LLMs love to hallucinate too. They are narrative-driven. They love to add plausible-sounding fluff just to make a paragraph flow better.
They absolutely do, which is why the prompt given to GPT-5 explicitly contains an exclusion rule.
An exclusion rule, so it's locked down.
Totally locked down. The prompt commands GPT-5 to aggressively remove any sentence or implied disease that is not explicitly in the trusted verified set provided by the SPL.
Wow, so it enforces clinical coherence over creative text generation. It's basically a factual cage for the LLM.
Exactly. It uses GPT-5 for perfect grammar and hospital formatting, but explicitly bans it from improvising new medical realities.
Okay, so the mechanics of GEAR and SPL sound amazing in theory, but the proof is in the X-rays. Does this actually work better than what we already have?
It absolutely crushed the state-of-the-art models. They tested this ESC-RL framework on 2 massive public chest X-ray datasets, MIMIC-CXR and IU-Xray.
And it beat models like 𝗏2Gen-RL and PROMPT-MRG.
And a very recent one called Ravitaf across the board. On MIMIC-CXR, it improved the green metric by a massive 5.0% when all the components were combined.
5%. In machine learning benchmarks, researchers usually fight for fractions of a percent.
Right, and keep in mind, green isn't like that flawed BLU score we talked about. Green leverages a language model to extract actual clinical entities. It evaluates if the generated report has the exact same clinically significant findings as the ground truth.
So it evaluates clinical efficacy, not just vocabulary overlap.
Exactly. And the qualitative examples really show what that 5% leap looks like. If you look at figure 3 in the study.
Oh yeah, the one with the highly complex chest scan where the older models just fell apart.
Right. Prompt MRG completely hallucinated a diagnosis of pulmonary vascular congestion, and 𝗟𝗘𝗔𝗥 missed subtle issues entirely.
But ESC-RL successfully captured a left retrocardiac atelectasis.
Which is incredibly impressive.
Yeah, for the non-medical listeners, that is essentially a partial lung collapse that is hidden almost completely behind the dense shadow of the heart. It's notoriously hard to spot, even for experienced humans.
And the model only caught it because the GEAR module aggressively penalized false negatives during training. It forced the visual encoders to really scrutinize those low contrast areas. Oh, and it managed to avoid hallucinating pulmonary edema, too.
So what does this all mean for you, the listener? I mean, if you or a loved one are ever in an ER waiting for a scan result, the bottleneck is always the sheer volume of scans in the queue. Technology like this means faster, highly accurate diagnoses without the risk of an AI making up a ghost illness.
Exactly. And what's fascinating here is that the researchers did an ablation study where they systematically turned off parts of the system to see what made it tick.
Right, to see if it was just GPT-5 doing all the heavy lifting.
Yes. And they proved it wasn't. When they removed the SPL module in GPT-5, the underlying clinical accuracy remained remarkably stable. The text was rougher, but it still identified the diseases correctly.
So without the GEAR and SPL framework, the LLM just makes the text sound prettier.
Exactly. True clinical accuracy requires the specific evidence-aware rewards. Oh, and the ablation study also found the sweet spot for the reward weight, the gamma hyperparameter.
Which was exactly at 0.5, right?
If you set gamma too high, the AI overthinks the visual evidence. It focuses so much on pixel boundaries that it can't string a sentence together.
And if it's too low, it just gets sloppy and prioritizes conversational language over facts.
Exactly. 0.5 is the perfect balance.
That's incredible. So just to briefly recap our journey today, we learned how the ESC-RL framework uses GEAR to force AI to point to visual evidence managing true positives, false negatives, and false positives.
Right.
And then it uses SPL to act as a chief resident, self-editing multiple drafts into one perfectly accurate, trustworthy medical report.
It's a huge step forward.
It really is. Any final thoughts before we wrap up today?
You know, I think this paper leaves us with a really broad philosophical question to mull over. It proves that AI is most powerful when we engineer it to systematically doubt its own initial conclusions.
Like a built-in automated self-doubt mechanism.
Exactly. If we can teach an AI to successfully self-correct its own medical diagnoses by explicitly hunting for its own false positives, what other high-stakes areas of our own lives could benefit from this?
Wow, like what?
Think about our news consumption or automated high-frequency trading in finance. If we mandated an automated self-doubt and evidence-checking mechanism in those algorithms before they acted, the reduction in informational hallucinations could be staggering.
That is a fascinating thought to leave on. Thank you so much for joining us on this deep dive. Keep questioning the algorithms, and we will catch you next time.